Let's look at a couple more examples of partial fraction decomposition. Write the partial fraction decomposition of the rational expression. Here we have x squared minus x minus 1 divided by x cubed plus x squared plus x. Again, we look at the degree of the numerator and the degree of the denominator. In this case, the degree of the numerator is less than the degree of the denominator, so we do not need to divide. If we don't need to divide, we can go on to factoring the denominator. Whenever we go to factor a polynomial, we should look for a greatest common factor. In this case, our greatest common factor is x. Factoring out an x leaves us with x squared minus x minus 1 divided by x times x squared plus x plus 1. One thing to make note here is that this is actually the completely factored form of the denominator. X squared plus x plus 1 cannot be factored any farther. The only factors of 1 are positive 1 and negative 1, and none of those combinations are going to add to give us 1, the coefficient in front of our x. Therefore, this is completely factored. Looking at our factors, we have two factors. That means we're going to have two fractions. One is linear and one is quadratic. Our linear factor will decompose into a constant divided by the linear factor, and our quadratic factor will decompose into a linear numerator, constant times x plus the next constant, over the quadratic factor. That leaves us with a over x plus bx plus c divided by x squared plus x plus 1. Again, linear factors create a constant in the numerator. Quadratic factors create a linear numerator, constant times x plus next constant. Now we need to solve for the constants a, b, and c. To get rid of all the fractions, we are going to multiply by the least common denominator. The least common denominator is simply the denominator of the original fraction. When we multiply the entire denominator, and x times x squared plus x plus 1 will cancel on the left-hand side of the equation, leaving us with x squared minus x minus 1. The x's will cancel when we multiply into this first fraction, leaving us with a times x squared plus x plus 1, and the x squared plus x plus 1's will cancel when we multiply by our second fraction. We end up with x squared minus x minus 1 equals a times the quantity x squared plus x plus 1 plus bx plus c. Notice I put all that in parentheses. That's the entire numerator here, times x. Once we do that, we can expand the expression by distributing in. Apply the distributive property of multiplication. That leaves us with x squared minus x minus 1 equals ax squared plus ax plus a plus bx squared plus cx. Once we do that, we want to group all our like terms of x, and it's helpful to write them in decreasing order of power. So our highest power is x squared. I have two x squared terms. I'm going to group those together. I have two x terms. I'm going to group those together. And I only have one term, this a, which has no x associated with it. I'm going to put that last. We have x squared minus x minus 1 equals ax squared plus bx squared plus ax plus cx plus a. Again, grouping like powers of x. That allows us to now factor out common factors in each one of these groupings. Here with a and b, I can factor out an x squared. That leaves me with the quantity a plus b times x squared. With this a and c grouping, I can factor out an x, leaving me with a plus c times x plus a at the end. Now, again, this equation must be true. The values on the left have to equal the values on the right. Well, how many x squareds are there? The coefficient in front of x squared is 1 on the left. Therefore, the coefficient in front of x squared must be 1 on the right. In other words, a plus b has to equal 1. The coefficient in front of the x term on the left is negative 1. That means that the coefficient in front of the x term on the right has to be negative 1. A plus c has to equal negative 1. And the constant term on the left-hand side is negative 1. Therefore, in this case, a must be equal to negative 1 on the right-hand side of the equation. Well, what did we just generate? Again, we have a system of equations, this time with three unknowns. The good news is we already know what a is. A is equal to -1, and we can back substitute that into each of our other two equations to solve for the other constant. Back substituting in the first one gives us -1 plus b is equal to 1, meaning that b is equal to 2. -1 plus c is equal to -1, meaning that c is equal to 0. And now that we have the values for a, b, and c, we can back substitute them into the form of our partial fraction decomposition to get our answer. Again, I think it's always helpful to begin by writing the original fraction. We have x squared minus x minus 1 over x cubed plus x squared plus x. That was our original. Broke down into, it equals a over x, that's -1 over x, plus bx plus c over x squared plus x plus 1. That's 2x plus 0 over x squared plus x plus 1. And to simplify our answer, yes, we don't have to worry about adding 0. We can get rid of that. Adding 0 doesn't change anything. And always helpful to put your positive term first. We can rewrite it. X squared minus x minus 1 over x cubed plus x squared plus x equals 2x over x squared plus x plus 1 minus 1 over x. Let's try one more. Write the partial fraction decomposition of the rational expression. Well, the degree of the numerator is 1. The degree of the denominator is 3. We do not need to divide. We can begin by factoring our denominator. Now, in this case, we have a cubic denominator, and this is actually going to factor by grouping. Let's begin by grouping our first two terms and our second two terms of the denominator. This leaves us with x plus 6 over x cubed plus 2x squared plus the quantity -3x minus 6. Again, grouping our first two terms and our last two terms of the denominator. Now we can factor out greatest common factors from each grouping. From my first grouping, I can factor out an x squared, and from my second grouping, I can factor out a -3. Doing so leaves me with, in the denominator, x squared times the quantity x plus 2 minus 3 times x plus 2. And whenever you're factoring by grouping, the goal is to have the exact same quantity inside of each one of these parentheses. This tells us that our factors are going to be x squared minus 3, here's my x squared minus 3, combination of those, times x plus 2. All right, so there is the factored form of the denominator for our rational expression. X plus 6 divided by x squared minus 3. So we have it factored. We're going to create some more space here. Now we can begin to break it apart. X squared minus 3, that is completely factored. So we recognize that this is a quadratic factor here. X plus 2 is a linear factor. Well, if I have a quadratic factor, that's going to decompose into a constant times x plus the next constant. And if I have a distinct linear factor, that's just going to be a constant divided by my linear factor. Ax plus b divided by x squared minus 3 plus c over x plus 2. Now that we have decomposed or written the form of the partial fraction decomposition, we need to solve for the constants a, b, and c. To do so, we multiply everything by the least common denominator. The least common denominator is the denominator of our original fraction, and it's helpful to write it in factored form. Notice all of those are going to cancel on the left-hand side of the equation, leaving us with x plus 6. The x squareds minus 3 will cancel with this first fraction, leaving us with ax plus b, the quantity ax plus b, times x squared minus 3. And the x plus 2's will cancel when we multiply by the second fraction here, leaving us with c times x squared minus 3. Now we have to distribute. We must expand. Well, when we expand, we're multiplying two binomials here. We must FOIL, or use the distributive property of multiplication. Same thing here, use the distributive property of multiplication. This leaves us with x plus 6 equals ax squared plus 2ax plus bx plus 2b. That's the multiplication of my first, my outer, my inner, and my last terms, plus cx squared minus 3c when I distribute in to these values. Once we expand, we group our like terms. Okay, group all your x squared terms, ax squared, cx squared, group all your x terms, 2ax, bx, and group all your terms that don't have an x associated with them. Write them in decreasing orders of powers. X plus 6 equals ax squared plus cx squared plus 2ax plus bx plus 2b minus 3c. Now that we have common factors of x squared in this grouping, we can factor out an x squared here. We have a common factor of x in these two pairs. We can factor out an x from those two, giving us x plus 6 equals a plus c times x squared plus 2a plus b times x plus 2b minus 3c. Well, in order for this equation to be true, the coefficients of all the terms on the left-hand side have to equal the coefficients of all the terms on the right-hand side. The constant on the left-hand side has to equal the constant on the right-hand side. On the left-hand side, we notice that there are 0 x squared terms. In order to have 0 x squared terms on the right-hand side, that would mean a plus c has to equal 0. There is 1x on the left-hand side of this equation. That means that the coefficient 2a plus b must be equal to 1. And the constant term on the left is 6. Well, all the other values that don't have an x associated with it, 2b minus 3c must be equal to 6. And again, we create another system of equations, this one with 3 variables and 3 unknowns. So, with a system of 3 variables and 3 unknowns, we want to simplify it down. In this first equation, we can begin by isolating a. A is equal to negative c. I can then substitute that into my second equation here, giving me 2 times negative c plus b is equal to 1, or b minus 2c is equal to 1. I can now combine that with my third equation by isolating b. B is equal to 1 plus 2c, and now I can substitute 1 plus 2c in for b into this third equation here. 2 times the quantity 1 plus 2c minus 3c is equal to 6. We do out our algebra. Distribute 2 plus 4c minus 3c equals 6. 4c minus 3c, well, that's just 1c. I subtract 2, leaving me with c is equal to 4. Now that I know c is equal to 4, I can solve for a. A is equal to negative c, which means that a must be equal to negative 4. And we can also now solve for b here. We have b is equal to 1 plus 2c. If c is 4, that means b is equal to 1 plus 2 times 4, or b is equal to 9. And there we have each one of our constants. A, B, and C. Once we have solved for the constants, we can back substitute them into the form of our partial fraction decomposition to give us our answer. We have x plus 6 divided by x cubed plus 2x squared minus 3x minus 6. Again, that's just our original expression. Our original rational expression is equal to, what did it break down into? Well, we had a, negative 4x plus b, 9 over x squared minus 3, plus c, which is 4, over x plus 2. 4 over x plus 2. And there we have our partial fraction decomposition. Again, this would be a perfectly acceptable final answer, but if you're really good and you don't like having these negatives in front, we can bring this 4 over x plus 2 in front of the negative 4x plus 9, in front of this first fraction, and factor out a negative 1. Now, if you're going to do that, you have to factor out a negative 1 from each term in the numerator. So to bring the negative in front of the fraction, it becomes a negative in front times, this would be a 4x minus 9 in the numerator. So x plus 6 divided by x cubed plus 2x squared minus 3x minus 6 equals 4 over x plus 2 minus 4x minus 9 over x squared minus 3. There is our partial fraction decomposition. And if we wanted to check our work, we most certainly could find a common denominator between these two fractions, subtract them, and we would end up with our original expression.